Hello, welcome to this Atos Life, our digital vision. Today, we are going to talk about digital banking and quantum computing. And yeah, at some point we thought like, okay, digital banking, quantum computing, how comes this together? Because sometimes in common minds, people think of quantum computing about huge algorithms, making or creating solutions for the biggest problem on earth, creating health models, creating environmental models. But yeah, the truth is that quantum computing initially is pioneered in the financial market. To be very honest, at some point, besides NFT, I'm at some points not really understanding quantum. And this is so great that I'm not alone today. So I'm very happy that I have Frederik Kerling on my side today, joining me for that session, who is very knowledgeable about quantum computing. And you are a quantum expert, Frederik, right?
Yes.
Yes. Well, that's simple, but maybe you can give us a short introduction about the yes,
Yeah.
which is a very efficient way of giving an answer, like a quantum computing would do. Huh?
Yeah. So I'm Frederik Kerling. I am currently head of fintech for Atos. I have a background in quantum physics. I actually used to design qubits in quantum computers.
Wow.
But I decided to be a bit more socially engaged. I became a consultant and then a quantum expert at Atos.
What does it mean to be a quantum expert? It's like right now, sometimes it's not that tangible for some people. Well, maybe what is quantum? What's a quantum consultant? What can you do with quantum right now?
So quantum, which is obviously a very abused term, but in our case, it means how do you deal with quantum technologies, which means that you use qubits rather than bits and to figure out how you can make useful applications of that and all of the application aspects around it. So the software, the hardware, the integration, the value streams, etc. It's quite
That's
broad.
very interesting. Well, for me, quantum computing, I learned about that. Well, people were just like writing articles about that quantum computing will totally change the blockchain and it could like recreate the blockchain in seconds. So all my non-existent Bitcoin would be at risk at some point. So that's why I switched into altcoins. But that's the same problem. But there's so much more than this, or?
Yeah, there's so much more. So it was originally thought of as a physics experiment. Then later on, more practical applications came along. And of course, nowadays it's seen really much as a solution to going beyond the exascale for certain problems, especially around healthcare, finance, but also logistics, that are really going to change our world.
Wow, that's really amazing. And just like as I am putting out questions for all you participants that are joining us live here on LinkedIn or either on YouTube, if you have a question, you can just place your question in the comment section. You can also comment on what you hear, and we might tackle those questions during the live. So just like feel free to place them into the chat area and we can bring them during that live session. But I think before that, Frederik, I would hand over to you and say like, please tell us a bit more about quantum computing, about what it means for the digital banking area, for the financial market. And it's like why we are here today for this great session.
Yes. Well, in order to do so, I've prepared some slides, which are going to help us to get through the actual presentation. So what I'm going to tell you today is a little bit about that first thing. How did we get here? How did finance become such a large part of quantum computing, such an active market in it at the moment? And I'm also going to explain that by giving an example of an actual application today, which can actually run today. That's why it's interesting. And also going to give you an example for the future. So what is it that's interesting to look out for? What's something you might not yet have heard in other media? And there's a little bit of scoop in there as well. So that's what I'll be talking to you about today. If you have questions, feel free to post them. We will answer them after the session. There can be many questions, even if it's just loosely regarded to quantum and finance, feel free to ask them.
Super.
All right. Then I'm going to go, Frida.
Yeah, absolutely great. Right. Let's jump into it.
So a short history. Where has it started? So the first data I really want to mention is Shor's and Grover's algorithms, which were originated in 1994 and 1996. The reason these are interesting is because these were the first algorithms that had practical applications. So rather than just having a simulator of physics, there were some actual tangible results coming from quantum computer other than physics. For instance, Shor is very famously known for being able to breaking the RSA encryption code, and Grover is a very famous database searching algorithm. Now, we as Atos, we actually have arrived in quantum as well, and we did so in 2010 already. when we did a so-called quantum key distribution pilot between two data centers of us in order to find some sort of new security measures against quantum attacks, which admittingly was perhaps a bit early. 2010, the largest quantum computer was 3 or 5 qubits, so it wasn't necessarily a threat to us. I can also assure you we didn't sell anything in this field yet, but it is one of our first steps into quantum as well. Then, of course, you have the Google AI Lab in 2013, where we see really some investments from a large commercial player starting to really work on quantum technologies and applying quantum computing. It's a big shift. But the biggest shift came a year later. And in this year, the biggest gate-based quantum computer was only 14 qubits, whereas the largest annealing quantum computer, which is a different kind of quantum computer, was only 84 qubits. So they're still very small, and there wasn't really a lot of practical application. But it was this year that the Commonwealth Bank of Australia started investing in the University of New South Wales silicon-based quantum computer, which is also one to keep looking at because it's a very nice design. This was really the first time we saw a large financial organization investing something. And at that time, there were no really focused financial use cases yet. But it's interesting to tell that in December, they invested just 5 million euros, and I think a year later, they invested about 10 times more. So by that time, they probably already figured out that there are some really useful use cases that could be run on this technology, even for their company. So this is really the first indication that we see an uptake of a commercial market for any kind of quantum technology. Before this, there were not really a lot of non-IT players that were working in the field. It's also the reason why we as Atos actually made a white paper about quantum finance opportunities back in 2015. It was published 2016 for various reasons of our own quantum program. But this is we first made the assessment saying, okay, we're looking at the financial market. What kind of possibilities are there for quantum computers? What do we already know? And how can we apply it? So if you actually read up this white paper, you can actually read some of the algorithms, which are, some of them are actually been tried by now. At that time they weren't, of course. We were trying to mix and match, and we really wanted to focus on these opportunities. We were saying quite early on that you, as a financial institution, you really need to have your own data team so that you are close to the business and you can try and establish what works and what doesn't work. And this is really nice. It's also one of the first papers which focus really strictly on opportunities. Of course, we suffered about 6 years of not being able of selling anything in the security part. So that's why we really want to focus on opportunities, also because we knew that is where the big money lies. Now, another big pivotal moment was the IBM quantum experience. It was in May 2016. And what that really meant is that suddenly all around the world, we saw an uptake in investments and engagement with quantum computing. It's really a very simple gateway-based open source platform, which is runs on old research computers from IBM, but it was really the first time people could experiment with the actual technology without having to be in a lab themselves. And we really saw a giant uptake in the adoption of the technology. Of course, we ourselves launched our program in November 2016, and also Microsoft did the same in the same month, where they actually made a very large call on the market. And then suddenly, basically, this starts the quantum race, where the big American companies start to race to create this quantum hardware and really become very large. Now, all of this are still just quite soft for the finance market. And the finance market really got engaged in June 2018 when Werner and Egger made their research called quantum risk analysis, which is a very specific application, very specific for the financial market. And from that date, we really saw that a lot of banks were suddenly starting to become active. They were starting to make their own programs. They're starting to invest and discover what really work up to today, whereas about 20 plus banks who have serious investment programs going to actually discover how kind of use cases can benefit them. Which of course leads to today, where, of course, the largest quantum computer commercially available at the moment is 127 qubits. And that means it has finally become a point where we can start to think about pushing things to production rather than just being at a research topic.
That's quite interesting. 127, just like to get sorted that I'm interrupting, but like to give a glimpse, what does it mean, like in calculation power? How can I relate it to, just like to my desktop PC? Let's say it like that, Matt, if that's possible.
127 is something, if you would want to simulate it, so like you want to simulate a quantum computer on a normal supercomputer, it could not be done with all of the supercomputers in the world presently.
Okay.
That might sound like a lot.
Well, yes,
but of course,
definitely.
but in practice, it really depends on how you apply those 127 qubits and how stable they are. So it's a really fine game of understanding how the computer looks like and how it works in order to actually use those 127 qubits. And it's not a trivial thing. It's not like you can plug and play. They're not like the computers we have on our phone where you can just run any program. It's really, really knowing how the computers work, how your software works, how to perfectly optimize that you can use those 127 to effect of such a powerful thing, more powerful than a normal supercomputer.
Wow. Thank you.
So, of course, the big question is now, so what does that practical solution looks like? So I prepared an example of how that looks today. So what is a practical implementation of a quantum computer in the finance sector look today? To do so, I'm going to attack value at risk. And those of you that already know a little bit about risk in the finance sector probably know this, but I'm going to repeat it for those that don't. So value at risk is very nicely defined on the screen by Investopia, and it basically means that you calculate how much cash must be reserved to cover that risks of the potential loss of your assets. So every financial institution has an amount of assets they manage. Those assets then can differ in value. Some of them become more valuable, some of them become less valuable. And the question is, how much loss do I need to cover in case that happens? For a single asset, this is just guesswork, of course. But if you're an asset manager of 200 billion euros of assets, this averages out pretty nicely. And it means how much of my cash I must keep in order to cover for those potential risks. Now, that also means that if I know how much I must keep in reserve in order to cover those potential losses, it also means how much free cash I have available for trade. So if I can do value at risk really quickly, I can be much closer to a market volatility, which means that I can have more free cash for trade, and therefore I can actually make more money because I simply have more of my assets I can put to work, and less of them I have to cover potential losses. It seems really simple, but in practice, it is not so simple. And the reason for that is how we calculate that value at risk at the moment. Because you can draw this graph, maybe even by hand for a single asset, but of course, if you have a 200 billion euro asset portfolio, you have more than one asset. So how is that done today in computers? Well, let's use a so-called Monte Carlo simulation. And on the screen, you see really how it's done. On the left, there is a random path. So a certain asset starts at a certain value at time span 0. What a supercomputer does is that it calculates random paths from that point. And it really does so point by point. So every single little corner you can see in the screen of every single colored line is one calculation in a supercomputer. And it does so over very many paths until it reaches that distribution on the right. And that distribution on the right is, the potential loss. And we really want to know just that one value. So let's say at 5% loss, how much do I need to cover? That's it. And the reason why we need supercomputers for that is exactly what you see on the screen. Every single step is calculated. So every single value of every single bar is noted somewhere in a very large table. You can do this one asset on your home computer if you want. You can even write it in Excel. I've actually done that once. It's a huge file, 50 megabytes for just this one thing. Now, of course, Excel might not be the most opportune system for that, but even if you use a good database program, just calculating this, it costs you about 5 megabytes just to get that one byte of information, because all that we are really interested in is that $620.50 value, because that's the one we want to know. And that's also the only thing that banks use. They calculate all of this stuff solely to find that value, and that value is then computed for the entire asset portfolio, and then they can have it working.
Right.
Yeah.
Sorry, I need to step in. It's like when I see all that, like all those single points or calculations, you were talking about like a normal spreadsheet calculation tools. How fast is it like to get an understanding, for example, that, that image looks pretty simple. It's like, how long does it take to calculate something in general, not always going on the fastest computer, but in a typical situation?
Yeah, that's actually a very good question. So this single calculation, if you do it on your home computer, few seconds. Might not seem a lot, but the problem is you don't have one asset. You have hundreds, thousands, maybe millions of assets. Some of them might be correlated or strongly correlated with one another. So if you want to do it for your entire asset portfolio, you need a supercomputer, and you need to run it an entire day just so that you know what kind of risk you need to cover for that day. And that's what's currently happening in all of the large financial institutes. They are running a lot of supercomputing power just to calculate their value at risk. And that also means that they cannot anticipate on market volatility, which happens within that 1 day time span. So if they calculate something at 12 o'clock, let's say at Amsterdam time or Paris time, and something happens at the closing of the markets at the other side of the world, then they're going to have to wait an entire day to actually be able to coping with the market volatility.
Wow.
And they all know this. So they put in large margins of cash in order to cover for potential and expected market volatility. And if you don't do that, you are looking at really substantial losses you're not equipped for. You can even go bankrupt. So that is really much the downside of the speed. It takes a lot of capacity and it goes really slow. And this is also why quantum computers are actually so efficient, because a quantum computer can do this as well. Well, not entirely, but they can reach that value. Because the reason why they're so fast is not that they do all of these steps really fast, it's that they don't actually compute every single step. It uses a different process to reach to this distribution. This distribution is not even observable, you can't measure it, but you use the algorithm to get to just that single value. And the reason why that's efficient is because that only takes a few seconds, maybe a few minutes, rather than an entire day. And that means that even today, even with a crappy quantum computer, you can do it much faster than the present day alternative.
Wow, that sounds amazing. And it creates way more less data waste in some way, or compute power that is, because of course you have to come to the result and you have to do each of the single steps. If you don't have to do all those single steps, you come to the result faster. That also saves in power overall and makes you more safe on the market. Huh?
So it allows you to better respond to market volatilities. It allows you to do more. I mean, rather than having to do one by day, you can actually start really anticipating for instance, your algorithmic trade on the market volatility and your value at risk. So you can actually make a few percentages more free cash available every day that you're allowed to be able of actually trading, which is a significant impact on your profitability. And that's very useful. And the reason indeed why it's so much quicker, I thought maybe I can explain in simple words why it's so much quicker. Because as you said, you don't actually store these values, but what is it that you do? And through this, actually going to return to this algorithm that I mentioned about Werner and Egger, because this is actually what they are about. Actually, they are about the right side. So finding the value in the distribution and not the left side. Of course, very smart, because the left side is the data that makes a financial organization unique. Everybody can do the right side, but how to get to those distributions, that's where the money is. So that's not publicly available always. So how does it work in a quantum computer? In a quantum computer, you have a classical computer, like we're using today. Sometimes, quite often, it's actually a special supercomputer, and it pushes an assignment to a quantum processing unit. So it runs basically the algorithm, and on the right you see a artist impression of this distribution. Of course, this is not actually visible. You cannot actually get this out. Well, you could, but then you would have to run it just as long as a normal computer, so you would lose the benefit. And it shares up distribution in blocks of ranges. So for instance, the most left range is 0 to 12%, and then there is 13 to 24%, etc. And for this range, it calculates the value. And I find this value, and I know that, for instance, 0 to 12%, that is a certain amount of money. So I feed back that information back into the classical computer. We start to reassign the job for the quantum computer, and it does it again. But this time, it has redefined the ranges in a certain way, so to focus on the actual value that we want to get a higher precision. I do the same thing again, and I can do this again and again and again until I reach the precision I want. Now, every time you run this, you are basically doing this value at risk calculation for a certain range, and you're doing it very fast. You do it in a few minutes, and then you redo it and you read it. So this entire process of reaching the same kind of accuracy is done in half an hour at best. And what's interesting is you see these bars. And at the moment, there are 6 bars, which means I need at least six possible quantum values in a quantum computer. And what's nice about a quantum computer is in order to have, for instance, 8 values, I only need 3 qubits in order to have those values, which means that I can run this program, let's say theoretically on logical qubits, maybe 20 qubits, which sounds very little, but of course we do need a lot of stability. And that's the big challenge. And that's why it's relevant nowadays, because now we have 127 qubits. We can expend quite a lot of them on enough stability in order to make this single run actually work. And of course, it is not sufficient enough to make very large distribution yet, but because we are optimizing how we work between that classical and that quantum computer, and we optimize this process in this hybrid computing platform, we can also actually get some benefit from a tangible benefit that actually contributes to some better results in your production environment today. And the reason why it works is because you are very good at trying to optimally use the software code and the hardware of the quantum computer as optimally as possible. And that is actually what we do at Atos.
Wow, that's amazing. On the one hand part, I thought, oh, wow, that's easy. I'm just like going now to make myself starting in big investment funds with some small money. On the other hand, the algorithm would tell me like, hey, Friese, you need to keep all your cash because it's just so little that it doesn't make sense to invest anywhere. Where could I start right now? I would not start like with a huge machine, and also in regards of money. Like what's the approach to quantum? Is it something you could say?
Well, this solution is mostly beneficial if you have a very large asset portfolio, because then you're restricted to that very long calculations and you need so much time. If you have a very tiny asset portfolio, the calculations are much quicker and you don't actually need a quantum computer. But the bigger and more complicated your portfolio is, the more beneficial it is to go to a quantum computer. So in that case, it's beneficial because the people that have large portfolios, they have the money to buy a quantum computer and they have the one to benefit. And those that don't, they don't need it. So it's fair.
Right.
But if you want to do for yourself, at the moment, there is not too much you can do because you don't need it yet. You don't need, if you're like a single investor, there is not too much you need to do this. It's really the large number games. It's where all of the parallelization is a waste of computing power. That's when the quantum computer is useful. Unless, of course, you're a hacker, because then you can break encryption. But other than that, for now, this is one of the few use cases that actually really work well in production and that have an actual value to contribute to the organization.
That's interesting. Well, to understand, I already lost my faith into starting up a business with my having finally my cryptos going up. Well, for me, it's like I'm also quantum computing. I'm always doing it wrong with no big decisions. So I invest and I see it falling down. So maybe quantum computers could learn by me. My decisions would be a great starting point for narrowing down what not to do. But what are the other benefits and where to go? I think you have prepared and brought a little bit.
I have one scoop. So for the short term, and that's like 1 or 2 years from now in 2 years, it's really still the same statement we made in 2015. If you want to have benefit from this, make sure that you have a team of data scientists who can work with quantum computers, preferably even people that know how to develop quantum software, and start putting them near to the business to actually achieve results. This is what JP Morgan did, this is what Goldman Sachs did, and they achieved very good results, and they are now moving towards this step where they can actually push things to production. If you do it half-baked, so you just have a pilot, you notice a lot of people might do a lot of pilots, but because they don't actually put those data scientists next to the business, they don't actually get the value out. So that is a big message. If you really want to have serious about this, invest in a small team. They're just scientists. They're not that expensive. They don't need that much material, actually, especially the quantum software development. It's only when you know that there's actually benefit that it becomes expensive. So the investment is not that large, but do it, put them next to business, and start rethinking some of your basic challenges. Because even some of the things you might have been doing for 20, 30 years with normal classical computing technologies, maybe there might be some new solutions there. We've done it as well with other clients as well. Sometimes just revisiting how you do something actually achieves you new results, even though it might not be with a quantum computer. but just because there's more than one technology available. So start doing that if you really want to benefit from it.
Perfect. Well, thank you for this, and I think that was a great advice. But looking, you brought the example of today, and I think you also brought the example of tomorrow, right?
Exactly. So what we said is in 2015 we made this prediction about what it's working, and I'm very happy that it turns out to be mostly right. So I'm going to make a prediction again, where we're going to be in the financial market now at 5 years from now. So this is a bit of a scoop. And to do so, I need to introduce a new technology, which is called the quantum internet. And it's basically like a regular internet, but rather than normal bits, I send qubits. Very simple. There is actually already a quantum internet running. There's a 4-node quantum internet running in the Netherlands. It's the first of its kind. And they're actually doing experiments on that, trying to develop protocols. And what a quantum internet does, other than actually sending quantum information, it provides so-called instantaneous correlation, which means that if I measure in The Hague a 1, I will also measure that 1 in Amsterdam. And the distance between it doesn't matter. So I will measure a 1 in Amsterdam and The Hague at the same time. But if I would put one of them on Earth and one on Mars, I will also measure 1 or 0 at the same time. I don't know if it's 1 or 0, but I know 100% sure that it's both the same result. And that means it's actually faster than light. It's not information because it's random, but it's instantaneous correlation. That's what a quantum network is very good at.
Wow.
And one of the major benefits is that there are useful use cases which you can run on these things, even if you have a very rudimentary quantum internet. Because for a quantum computer, you need a few hundred qubits to run the algorithm for stability checks. But a raw NV center, which is used for qubit storage in quantum internet, has stability times over an hour, which is a million times longer than what is presently available in quantum computers. So the time when quantum computers become largely available and actually start to really benefit in multiple industries is also the time the quantum internet is becoming available. And that is something to pay attention to. So how does this affect the financial market? To do this, there's a very simple game. It's called CHSH game, named after famous inequality. And it's very simple. On the right, we have Bob. On the left, we have Alice. And Bob and Alice are both asked a certain question, X and Y. For simplicity, that question is either a 1 or a 0. Okay. And Alice and Bob respond with also, again, a 1 or 0. Very easy bit play. Now, they win the game if X times Y equals A plus B, which basically means that if the product of the question is same as the sum of the answers. And they can communicate with each other because we're in the same room, and they devise a strategy in order to win that game. But the moment the game starts, they cannot communicate anymore. These are the rules of the game, but in practice, let's say Alice stays on Earth and Bob goes to Mars, and the game only lasts for 2 minutes. Light travels over 15 minutes, so they really cannot communicate. And the trick is, how can they win at this game? Now, it turns out, if you do this, the best classical strategy has a 75% win probability of winning this game. However, if Bob and Alice have a quantum internet available, of course, they cannot exchange information, but they can exchange correlation. And if you take that into account of strategy, the highest win probability is now 85.4%. Wow. Now, these are non-local statistical strategies, and I do not know how it will impact our finance world. I do know that the rules of the game will change. And if you look at, for instance, algorithmic trade, it means that those rules will change as well. And since 90% of world trade is algorithmic trade, and if we know those statistical rules will change, so will the strategies. And if they change, so will how we do about 90% of our global trade. And we don't know, but I do believe it's something we must figure out how it impacts us. And I'll leave you with that question.
Wow, that's perfect and quite impressive. And just like to see very simple that you, just like with that simple example you gave, could have a gain of more than 10% in accuracy or to say like in the win probability. I think that's huge in the financial market. I mean, 10% being more accurate than any other one, that's just like sort of a game changer, right?
Yeah. Definitely. Wow. And it's also much simpler because it's just, you're just playing with simple bits. It's easier than quantum computing.
Wow, that's amazing. Well, in regards to the question, you say you leave me with that question, but there was also one question coming in, want to see like, once a bank has a well-developed use case like that, what options do they have to actually use quantum computing for it? Not each being a bank will invest in quantum computers right away. Is there a quantum computing as a service offered or how to approach that?
Yeah, that's a good question. It's also not very easy because if you have a quantum computer, let's say you have direct access to a quantum computer, because most of them are available via cloud, and you send a batch and you get a response. But if you have the actual computer available and you manage to get this hybrid computing done really well, optimize it both for your software code and hardware code, you can use it much quicker than if you just use it as a service. And if you look at all the quantum computing services which are available now, which is primarily IBM, you actually need to share all of your code with them in order for them to execute it. And if you are doing it, for instance, with trade information, I'm not sure that's even legal to do so. And so you cannot use those quantum computing as a service for those applications. You need to have direct access to quantum computing, because otherwise you're breaking the law. For them, they will need to buy, but then again, for them, the gains are very high. Quantum computers, a few million euros, but that's something you win back in a week. So the investment is worth it. But if you're doing it just for trying out, just use the services that are available. They're simple, and I'm quite certain that over time, when more quantum computers become available, you'll just have it in the cloud just as you have any other supercomputer at the moment.
Mm-hmm. Makes sense. Well, I don't have those few millions left. I just like put it here, not even in the business technology and innovation centers where we do the workshop with customers. Would be a great approach to have that here locally. But you mentioned something also about my QLM. It's like the initial approach. How can I try it? How can I get like hands-on? And we also have a link on that, right? Maybe you could tell us a bit more about that.
So our platform, of course, what we develop specializes really in a quite complicated task of putting something to production, which is really much an advanced use case. But the platform itself is, because of that, quite advanced. Rather than that you shuffle around with gates, it's just basically a Python programming language, which is really mature, and you can actually learn about it. So you can't use it to the optimal use which you want to actually run a use case, but you can use it to pre-program, you can use it to learn. It's really available, and it's really easy. It's actually very easy to learn. We always thought it would take months for someone to learn quantum computing. Turns out if you know Python, you can do it in 2 weeks, and you can be very good at it as well. So that's why MyQLM is something really nice. And you can communicate with any other large quantum programming language as well. It's very universal. I can highly recommend it.
That's perfect. That's perfect. We just brought up the link here to where you can find all the information on the My Quantum Learning Machine. And yes, you might say, oh, I cannot click the link on the video. Right now, we just also posted that into the chat here. You see, time is running, and quantum is such a huge topic. We had some comments coming in here, and it's like very interesting. There will be a huge achievement over the next couple of years. Now, what do you think? Like you said, 127 qubits, if I'm right. What would be your estimates for 22, 23?
Well, there's a roadmap from the actual producers. Okay. So we're looking at about 1,000 qubits within a year or 1.5. So by then, there are many more use cases available. It will not be long before most use cases we thought of 5 years ago are available in real life. Going really quickly now.
Yeah, well, that's great. It's always like how it starts, like slowly, and then it just like raises up the numbers. When I remember my first desktop computer, I mean, nobody knows how to use a floppy disk anymore, or even what the word is. But that's the thing, how things are going. But on quantum computing, maybe just like, what are the top 3 myths you would say, like rumors going around on quantum computing? Is there something you would say?
Yeah. So one very harsh one is still that people think that it's something far in the future. And that's something that's not available to them. And even if it is, you can't do anything with it. It's true that if you just look at the quantum computer itself, it's not going to do much. But if you are good at playing with, a classical computer or even an AI or neural network and the combination of multiple technologies, then it becomes very quickly, very powerful. And that's relevant today. Also, a lot of people talk about this quantum supremacy, saying that it's, if you reach quantum supremacy, you've beaten classical computers. It's a bit of an empty term. It doesn't really exist because what is supremacy if you can't do anything practical with it? But now we are reaching actual practical use cases, which are far more interesting than just some empty term. And that is really things to watch, because those are going to impact, and they're going to impact our markets, which we are doing today. And I'd say the third one is one that I used to have as well. And the third one is that it's very complicated, because even when we started for the first time training new people in this, because when I started out, I was the only person in Atos that knew anything about it, but by now there's research group, postdoc, PhD. So and a lot of programmers. And we always thought it would be very difficult to teach this to people, but it's not. Because it's just like when you learn a programming language, you just start entering stuff and you start getting results, and then you learn how it works. And that's the same with quantum computers. Sure, the logics are different, but for us humans, it's actually very easy. Our brains can comprehend it very easily. You just start trying. And now we can, because we have the programming language, we have the computers, we can start trying. And this is something incredibly easy. It's a bit harder for you and me because we're a little older. Well, probably for you because I've done it all my life. But I can just do 11, 12-year-old in a few weeks, and they can just walk away with it. It's very easy. And don't see it as a hurdle. It's easy as learning a programming language, and that's it.
Okay, so I'll try to do my Hello World on quantum computing next week, and if I'm still in search for that missing semicolon, I will just get in contact with you directly. Also, it's where can we get in contact with you? Everyone, all the participants, can follow you on LinkedIn. So you are active writing a lot of articles on quantum computing. You're communicating on LinkedIn about quantum computing. So to follow that would be an advice. I think that's great. Anything else you want to give away to the audience today that are still listening, even as we are in overtime, which is great? Thank you.
I would say if you really want to be serious about it, read the original white paper, make a plan. You can contact us as well if you want to build up a strategy around it. Find some good partners. There's a lot of good startups out there as well, a lot of enthusiastic people. But whatever you do, make sure that you do this very close to your core business where the actual value lies. It's not a solely technological exercise. You really need to understand your own business and understand the challenges that provide value to your organization. And that's where quantum can really benefit. It's not just technology. It's not just something for data scientists. It's really taking a new look at your core business. And that's where that's where your great benefits lie.
Perfect. Thank you very much for this. And thank you also for being the first one in this series of our digital vision journey today with quantum. And we started with quite a topic on that. Thank you so much for being with us and taking your times and all the answers. The question part will still be open. If you have questions afterwards, you can also place them and we will have a look at them. Thank you for being with us today, Frederik. Have a great day. And let's see what quantum brings us in the next year. If you have any more questions about quantum computing, what it can do for digital banking, but also for other areas, feel free to reach out. Just place a comment here in the section right here after or behind the video. And be sure that we will come up with another great informational session on our digital vision. Besides that, thank you for watching us. Have a great day. Thank you, everyone, and bye-bye.